Okay, in this video we'll talk about the consequences of betting repeatedly on roulette. So in roulette, betting on a single number, the chance of winning is 1 out of 38. And if you lose $1. If you win $35. Meaning that you bet $1, if you win, you get your dollar back plus 35 more for a net of 35. Okay, so let's figure out the expected value of x, and the standard deviation of x is the amount that you win playing the game once. So the probability of coming out ahead with $35 is 1 out of 38. The chance of losing $1 is 37 out of 38. And therefore, the expected value of x is equal to 35 times 1 over 38 plus -1 times 37 over 38. And that works out to be -2 over 38, which is -1/19. To find the standard deviation, we figure out the expected value of x squared. So that's 35 squared times 1 over 38 plus -1 squared times 37 over 38. And doing the arithmetic, we get 1,262 divided by 38. And finally, the standard deviation of x would therefore be equal to the square root of 1,262 divided by 38 minus -1/19 squared, the expected value of x squared minus the mean squared. And then plugging into a calculator, we get this is approximately 5.76279. Okay, so that's the expected value of x, the standard deviation of x, playing the game once. For part 2, it's a little bit more interesting. Let's suppose we play the game a bunch of times, 2,500 times. Find the expected value of y and the standard deviation of y. Now, one way to do this problem, which would be extremely painful, which would be to list out all the possible outcomes and the probabilities for each. Just like we did here, we listed out the possible outcomes and the probabilities for each. The good news is that y is the total if you play the game 2,500 times. And we have a rule that says that if you have the same type of random variable, independent and identically distributed, and add them all up, so y is equal to x1 through x 2,500, playing the game 2,500 times, then the expected value of y is equal to 2,500 times expected value of x. So that works out to be -2,500 over 19, which is about -$131.58. So playing the game 2,500 times, you expect to lose $131.58. The standard deviation of y is equal to the square root of 2,500 times the standard deviation of x. So the expected value gets multiplied by 2,500, the standard deviation gets multiplied by the square root of 2,500. So that works out to be 50 times 5.76279, and that's about $288.14. Okay, the third part of the problem. Suppose, what's the probability of coming out ahead, of having a positive net gain if you play the game 2,500 times? So the probability that y is greater than 0. By the central limit theorem, that is approximately the probability that a standard random variable is greater than 0 minus the mean, -131.58, divided by the standard deviation, which is 288.14. So that's the probability that z is greater than 0.45666. And then using technology or the bell curve, we can find that this is equal to 0.32396. That the area under the bell curve to the right of 0.4566, the area to the right is equal to about 32.4%. Not surprisingly, the answer is less than 50% because the odds are stacked against the gambler. However, the answer is not microscopic either. You can play the game for a very long time and there is a realistic chance of coming out ahead. So that's kind of the appeal of gambling, that you can play this game for a lot of times, and even though the odds are stacked against you, there is a realistic chance of coming out ahead, even though it's less than 50%.